Good evening. My name is Halil Ceylan. I'm a faculty member at Iowa State University. I serve as the chair of the Geo-Institute Payments Committee, and I'm here to present Dr. Tutumluer for his 2021 Monismith Lecture. He's a very well-known figure, but I know there's a very strong attendance on YouTube, and we have a lot of new faces. So if you do not mind, I will actually read his bio, and then the lecture will start. So Dr. Tutumluer is Abel Bliss Professor, specializing in transportation geotechnics in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. And he holds Paul F. Kent Endowed Faculty Scholar and serves as the Director of International and Zhejiang University Education Programs. Dr. Tutumluer's research interests and expertise in characterization of pavement and railroad track geomaterials, subgrade soils and base ballast, unbound aggregates, soil aggregate stabilization, geosynthetics, applications of artificial intelligence and deep learning techniques to transportation infrastructure, structural health monitoring of transportation facilities using sensors, modeling granular foundation systems using innovative techniques, sustainable use of foundation geomaterials, and construction practices for transportation infrastructure. And he's been also using discrete element analysis of ballast, dynamic response measurement, and analysis of track systems, and mechanistic analysis and design. Dr. Tutumluer has served as an investigator on over 100 research projects and graduated 22 PhD and 44 master students. You're looking at one of those proud PhD graduates from Dr. Tutumluer's academic family. And he has co-authored over 350 peer-reviewed publications from his research projects. He is a founding editor-in-chief of the Transportation Geotechnics Elsevier Journal and the current chair of the ISSMGE Technical Committee 202 on Transportation Geotechnics. Dr. Tutumluer is a member of the ASCE TNDI and Geo-Institute and served as the chair of the ASCE Geo-Institute's Payments Committee in 2016 and 12. He is a member of the AREMA Committee 1 on Ballast and council member and publication committee chair of the International Geosynthetic Society. He's an active affiliate of the Transportation Research Board and serves as the chair of the TRB's AKGOO Geology and Geotechnical Engineering section. He served as the chair of the TRB's AAP 70 Aggregates Committee in 2011 to 2016, and he is the 2000 recipient of the TRB's Fred Burgraff Award for Excellence in Transportation Research. He also received TRB's Geology and Earth Materials Section Best Paper Awards in 2009, 12, and 2019, and TRB's Soil Mechanics Section Best Paper Award in 2016. He was selected and honored with Yangtze River Scholar Award by China Ministry of Education in 2016 and Kushi Distinguished Professor title by Zhejiang University, and delivered the Zhangguoxi Honor Lecture in China in 2019. Dr. Tutumluer is the 2020 recipient of the ASCE TNDI James Lowry Prize in recognition of his career accomplishments for promoting transportation geotechnics field, and the 2021 recipient of ASCE Geo-Institute's Monismith Lecture Awards. Erol, thank you for your outstanding contributions on geotechnical aspects of payment systems and for all your mentoring and support over the years. With that, it is my greatest honor to present Dr. Tutumluer.
Good evening, everyone. It's great to have everyone here, and it's a great moment for me, for sure. So, but before I start, I'd like to mention that Halil has done such a great job in his career, accomplished so much already in his early career that it was a very nice introduction. Thank you, Halil, and indeed, really very proud of your accomplishments. With that, it's a great honor for me to stand in front of you and to present actually the 10th Carl L. Monismith Lecture Award today. Indeed, especially it's important for me to be here in front of you after Professor Carl Monismith himself in 2012, he presented the first lecture. This is the first time at a Geo-Congress venue that I'm actually presenting this award. And you will see that I go back in my roots in to geotechnical engineering with close ties. So with that said, those close ties really relate to some of the shallowest foundations of pavements as unbound aggregate sub-base layers, which is something that I've been working on since, I guess, I started my PhD work at Georgia Tech, and really owe it to Geo-Congress 2022 people who allowed me to actually present this lecture award at this time. Thank you again for the organizers, and thank you the technical committee for nominating me, as well as the board of directors with Geo-Institute. I do a lot of pavement work I will talk about today, but I'd like to also mention to you one logo on this title slide, which is there is an Academy of Pavement Science and Engineering established with the goal to actually educate, give higher education to people, to make them realize actually that pavement science and engineering is a field we need to learn more about, because, again, it is the shallowest foundation after all. And from that perspective, I've done a lot of work with Illinois Center for Transportation, and you will see that my slides will come up. So let me switch to using this right here, hopefully. There you go. But on the Pavements Committee, established back in 1997, you will see the focus is here, as mentioned, geotechnical aspects of pavements and essential use of geotechnical engineering principles in pavement engineering, and the need to bridge any knowledge gap. In my opinion, there shouldn't be any knowledge gap. In my opinion, every pavement engineer should have geotechnical engineering background, because we're building one of the toughest foundations, the shallowest foundations again. And from that perspective, throughout our work with the Pavements Committee, where I found a real home after I started my career at the University of Illinois, we've been answering a lot of calls on, tackling tough topics in pavement engineering and producing these great publications, the knowledge base in general. And as part of that, I think we've been quite involved in doing things. Even 2010, the committee won the Committee of the Year award, which I was very happy to actually have this award during my time when I was doing the president or the chairing of the Pavements Committee. Another thing that made me extremely proud at that time, again, towards the end of 2011 or so, when we established for the first time a named lecture, Carl L. Monismith Lecture series in pavement engineering here by the Geo-Institute. Professor Carl Monismith is a legend in our field. He's a distinguished member of ASCE. He's a National Academy member of Engineering member, and certainly served on the faculty of Berkeley, University of California, Berkeley, more than 50 years. His first talk on Monismith Lecture actually was exactly on flexible pavement analysis and design, a half a century of achievements here. So he's the one who pioneered the mechanistic approach to flexible asphalt pavement design. And I was there in that moment because with two other colleagues, Professor Tom Papagiannakis and Professor Chuck Schwartz, I indeed worked hard to make that award possible during that time. It's such a proud moment now, actually. I'm giving you this lecture because I was there to listen to Professor Monismith's lecture back in 2012 in the Oakland Geo-Congress event. It was a fantastic lecture, as expected, and especially students, Dr. Gary Hicks, Dr. Rita Leahy, they were very influential actually in bringing and getting this support for his lecture establishment. I would like to mention that. So he's certainly a legend. He was the person who gave the first lecture in this series in 2012. Just a quick pictures of deserving, highly accomplished people and legends in our field, again, in pavement engineering. Professor Bob Litton from Texas A&M gave the second one. Professor Marshall Thompson from University of Illinois. Many of you know him very well. Professor Matt Witzak, another legend, another name in pavement engineering, unfortunately passed away just a couple months ago. That was a tragic loss, and my heartfelt condolences to his family and friends. He gave the fourth one from Arizona State University. The fifth was given by Professor Dallas Little, and again, another deserving individual from Texas A&M University. Introduced him actually at that Chicago event, I remember. Dr. David Anderson from Penn State, who's done a lot of work on asphalt, especially Dr. Gary Hicks, I will mention about him again, a student of Professor Monismith's. Tom Papagiannakis, University of Texas San Antonio. And finally, the last one was given by Professor Chuck Schwartz of University of Maryland. Now, I'm giving the 10th one, and we already have an 11th one for 2022. Iyad Masad, Professor Masad is here with us. He's also from Texas A&M Qatar University. We're looking forward to his presentation next year. A little bit about myself. I said I have strong geotechnical engineering roots and background here. Indeed, I did all my PhD work and graduate studies at Georgia Tech. Dick Barksdale, Professor Dick Barksdale was my advisor, who was actually a student of Professor Jerry Leonard's, another legend in geotechnical engineering at Purdue University. And even going back to the academic family tree here, Professor Ralph Fadum, who was there for a short time, but also he was an advisor of Professor Jerry Leonard's, who moved from Canada to study at Purdue at that time. But eventually, Dr. Ralph Fadum was a professor at North Carolina State, right here in this state, actually. And he had education received from Casa Grande and Terzaghi at Harvard University. So really, that puts me, in that chain, and I'm very proud of that. But the moment that I first attended in 1994 as a grad student, my first Transportation Research Board meeting, that was a really life-changing moment for me, because that conference, and when I met for the first time Professor Carl Monismith, that's what really got me in academia. I can tell that was really the moment for me. Yes, I want to do more of this, doing research and studying and educating students. So that's why I have to mention. Now, after 2012, I went on the international front, and actually I've become the chair of, I was already working on the Transportation Geotechnics Committee affiliation and related work with the ISSMG. Since then, I've been serving as the chair of Transportation Geotechnics actually committee, TC202 under ISSMG. As part of that, we started a new journal in 2013 on transportation geotechnics. I think it's got into the citation index, and it's really making some good impact to our profession and engineering field in transportation geotechnics. I was also the person who did a unfortunately virtual conference meant to be in Chicago back in May 2021, and that was the fourth ICTG. I know we have an ISSMG conference coming up in May. So without further ado, let me get into my primary topics here, technical topics. I would like to bring to your appreciation actually some of the important facts and challenges we deal with in pavement engineering. And as part of that, my title has to do with dynamic loading and repeated loading and vehicular traffic loading. Indeed, what that does to our foundation materials and pavement materials, and how we take into their resilient or elastic behavior and permanent deformation behavior by understanding proper advanced characterization of their nonlinear stress-dependent and isotropic behavior, all the things that are supposed to be there for our doing a proper job in analyzing pavements, the layered pavement system. Moving wheel loads, not currently emphasized, very important. I will get into those aspects you will see. And nowadays, more and more recycled material use, sustainability challenges, climatic effects, and resiliency, how we can build pavements to last with the aspects that we want to preserve resources, right? Path forward, more we're getting into mobility 4.0. You probably heard about that term. Intelligent construction, smart mobility, and I will also give some highlights about those towards the end. To start with, have you ever thought about why Roman roads lasted that long? They built about 53,000 miles of roads 2,000 years ago. About 360 miles or so of roads still exist today. When you look down deeper, actually, in that 3 to 5 feet thick Roman roads, you will find that different size aggregates put together to build a road, a lifeline that we drive on nowadays. The same thing was the case when first macadam road came to the United States in Maryland in the 1800s, right here. Same thing. See how they're putting, incising and putting rocks together. These are the aggregates, right? Our stone skeleton infrastructure materials, building blocks. Recently, in 2013, we did an NCHRP, National Cooperative Highway Research Program, synthesis on unbound aggregate pavement layers, and it was quite interesting, and as expected, over 90% of pavements, flexible pavements, these are asphalt surface pavements, they have granular layers. This number goes up to 70% in the case of rigid pavements, and that means we built with unbound aggregate layers, as you see from these statistics, all the time, except for, I guess, some of the high-type pavements. 90% of, or more than 90% of the 4 million miles of roads in the United States will have these unbound aggregate layers. Understanding their behavior really helps us building long-lasting pavements. That's how throughout the activities of the Pavements Committee over the years, again, starting from the late 1990s, we put emphasis on geotechnical aspects of pavements. This is a Geostrata article from 2016, Drs. Barry Christopher and Chuck Schwartz and I co-authored, which shows actually the Asher road test many of you are familiar with. And unfortunately, many of you are familiar with that cookbook formula that comes with the structural number equation. There's much more to pavements than that, believe me. It is not an easy thing building pavements. In fact, when you think about the multi-layered pavements, just like a conventional flexible pavement you see here with the typical unbound aggregate base and subbase, and how to make it both drainable and packed, optimum packing with large or small or different sizes of particles to distribute the load, how to make that actually last. We are indeed, as pavement engineers, designing something to fail in a certain number of years. You don't do that in any other job. You don't build a steel structure to fail, to kill people at some point, right? But roads are failing on a certain time frame, and they have a time life, basically. So it's really challenging when you think about the dynamic loading aspects, the climatic conditions, environment, right? Moisture and temperature changing on you all the time, and of course the construction aspects, hoping that you're constructing what you designed. So flexible pavement is an asphalt surface pavement. Load distribution in those aggregate layers are very important. Modulus, stiffness, resistance to permanent deformation, all those things you have to pay attention under a dynamic loading scenario when you're constructing them. In the case of rigid pavements, these are often jointed concrete pavements and slabs, right? The slab action, they're sitting on, slabs are very stiff, 10 times more, maybe an order of magnitude stiffer than asphalt concrete surface. So more the focus in unbound aggregate layers go to some of the moisture affinity and drainage aspects, right? Looking at their moisture, whether or not they're susceptible to moisture effects, the suction potentials, their hydraulic conductivity properties, that's what we should be paying more attention. That all come back to, these particles put together as unbound aggregate layers, an assembly, which just like our soils have three-phase material, voids, how much of the voids filled with water, right? We need to be engineering these such that eventually the roads will perform and not deform and not rot, and they will still be able to freely drain and all those aspects. So it's really a challenge. And in all this, the design objective is the surface that you're driving on is still supposed to provide for you a smooth and safe and durable you know, riding environment, right? That's eventually the design objective. But don't forget about the challenges of constantly moving vehicular loads, sometimes heavier than what is expected on a certain road, the effects of moisture and temperature and seasonal changes, as well as extreme events we'll talk about, weak pavement foundations, that's where we come in, right? Again, load carrying capacity, safety, serviceability, more and more these days sustainability aspects, and all of a sudden, of course, the permanency, resiliency that comes with life cycle cost estimation into the picture. Most of the time, when you remember the empirical Ashto equation, the structural number, right? That's how everything goes back to the 1960s Asher road test, but so much has changed since then. So we need to really design multi-layer pavements by understanding the mechanisms about how they deform and how they fail, right? And understanding those mechanisms requires our right inputs as the traffic loading, the climatic factors, temperature, moisture regimes, and as well as the construction aspects. We need to bring them all together. We need to solve the multi-layer structure, how the various layers coming together are going to take the load, right? And what are the responses? Usually stresses, strains, deformations, these are pavement responses. What is a critical pavement response that's going to cause a cracking, that's going to cause rutting? Which layer is rutting? You need to understand these mechanisms to eventually relate them with the number of load accumulation, how damage accumulates, right? These are distresses like alligator cracking, fatigue cracking, or roughness of the pavement surfaces, or rutting in the wheel pad, right? And this is a process, we call it mechanistic empirical design as the state of the art. We need to really understand this. Well, understanding this and perfecting this really relates to going to a level that you need to characterize the right stress states, you need to apply the right kind of loading scenarios and conditions in the lab on your samples and specimens you test and analyze, right? That's the lab testing at the level. You need to do field trials. Well, field trials will not probably complete so many truckloads, so much traffic that you will accumulate in the 20-year design life of that pavement. You need to actually accelerate that performance period, maybe doing accelerated pavement testing in the field, full-scale construction of those pavements, and the modeling, the right modeling by understanding the mechanisms. So that's all what's needed. In all of this, of course, performance, and performance is a must. It must be satisfactory to come up with your guidelines and specifications for construction. Now, think about this as a single wheel. Single wheel traversing over on in this case, an aggregate layer, right? Often construction platforms these are, and understanding the type of contact stresses, right, in the vertical direction, longitudinal, transverse directions. And what if you go from a standard dual wheel or single wheel to a wide base tire? You know, what are the implications of those on a pavement surface? And this is just a single wheel. Think about it now. These are 13 vehicle classes of the Federal Highway Administration. These are all the different trucks, buses, cars, all the vehicles you see out on the pavement, right? How do you take this into account? How do you accumulate traffic? How do you look at effects? The same thing is in the case of airfield pavements. How do you look at closely spaced many wheels, you know, actually applying a very heavy load from that wide-body aircraft, right? Really challenging. And, you know, all in all, again, this is a moving wheel load aspect. So nowadays what we do is, some of you may have heard this, weigh-in-motion stations, usually in states. That's where they collect the data, and that's what easily goes back to a mechanistic empirical design approach where we take into account every single axle and the load coming from every single axle wheel arrangement. That's how axle load spectra are established. But there are other things that we have to worry about on the surface, from the point of road alignment, pavement friction, hydrodynamic forces that affect the vehicle control, and how all of that come into that vehicular stability. So there are things really that are complicated dynamic loading. It's not earthquake loading, but this is another dynamic loading, right? We are challenged here. in geotechnical engineering, pavement geotechnics. So in all of this, state-of-the-art goes to your three-dimensional finite element programming. Professor Al-Qadi, my colleague, director of ICT, he does a great job taking into account, some of the really advanced topics. For example, viscoelastic properties of asphalt, right? All those things by characterizing properly in the lab. I joined with him by actually looking at base and subgrade materials from the databases like long-term pavement performance studies. But looking at where the rubber meets asphalt, right? Exactly, we need to understand that contact stresses, moving load effects, how load is transmitted, and how multiple layers are interacting with each other, any delaminations, any interface stresses. Of course, all those things we assume perfectly bonded and perfectly fine, perfect conditions in most of our analyses, right? But again, that's something state-of-the-art. When you come and look at the aspects of under that surface course again, under that asphalt concrete, flexible pavements, low to medium volume roads, thick airport pavements with thick granular layers, always load stress distribution is the key, as I mentioned before. And load has to be distributed because subgrade is the weakest component. You want to protect it, right? That's the whole idea. So layer modulus is a design input. That's how you solve for pavement responses. Strength and deformation are there, though, that need to be there because that road and that unbound aggregate layer should resist the effects of multiple repetitions of a certain truck passing on that road, right? Again, dynamic loading aspects. Let's get into the shallow foundation domain and understand the typical stress states under a wheel, right? We're very familiar with this. There's an overburden load right on that, and if you look at a certain soil element or aggregate element right in that base course, typically you are confined in a confined medium, but not a lot of overburden we have. The only thing that comes as dynamic is usually that wheel loading. If you put the wheel right on top, there are things you can do like jump up and down the wheel, but that's not the fact. Wheels are moving in nature, but somehow there is some dynamic impact loading that may take place. You need to take into account all of those things. That's how the repeated load triaxial tests are designed to evaluate dynamic traffic loading effects on typical triaxial specimens, which as geotechnical engineers we commonly run these tests on, right? But this is different from a cyclic loading test because in between the different wheels, axles of a truck, right, you have some wait times, rest periods. So that's why it's called a repeated load. We always have a rest period in between, waiting for the material to bounce back, right? And indeed, that's very important, that bouncing back. This is the only video that I think I have not worked very well. The material, the specimen that you see in the picture is supposed to be going up and down with the wheel passing on top, right? That's exactly the recoverable deformation or the unload behavior, the elastic deformation. That's what we are using to define our resilient modulus. If you heard the term resilient modulus, it is nothing different than any elastic modulus, right? They're from the same family, but when you hear resilient modulus, always remember that this is an elastic behavior, elastic modulus obtained on a deformed shape. That means at the end of that loop, load-unload loop, it doesn't come back to origin, zero. There's a permanent deformation that's accumulating in time, and you can clearly see that on the lower left picture, the permanent deformation is accumulating in time. You want to make sure to accumulate that up front before you open the road to traffic during construction, right? That's the idea. But anyway, dynamic loading, deviator stress divided by recoverable strain, that's your modulus. We typically run the ASCE T307 test in the US to get this, and this is basically the resilient modulus test procedure that came out of the Strategic Highway Research Program protocol. Also, NCHRP study 1-28 brought us some special aspects that actually Europeans are already using, which is they're taking into account moving wheel load aspects. With a moving wheel load, you get variable confining pressure conditions. The load is moving already. The load is not stationary, right? So that's why as I differentiate these triaxial setups, if the cell pressure is constantly applied, that's a constant confining, versus variable confining would represent a moving wheel, right? So again, typical standards, the European SEN norm, for example, applies that. Other countries in Europe can apply that. So we need to be doing more of that. Whereas in the US, this is from 2013 synthesis, we found only 4 states to run even the 307 procedure in their DOT, Departments of Transportation labs. So interestingly, it's just the T307 or the 1-28A. The only difference is on these plots, you see the vertical stress versus horizontal stress. Basically, the bottom one, she's showing that horizontal and vertical stress, they're increasing together. Imagine a moving load, a load is coming, approaching, that's exactly what's happening. That pavement element, that soil element will feel the load coming from both vertical and horizontal directions, and we need to take that properly into account. Although most of the time we assume wheel is directly on top, constant confining, only the repeated loading coming from the vertical, and we apply typically 15 different stress states with 5 different confining pressures and 3 different deviator stresses, right? That's the typical results of a crushed stone and the sand at the bottom part. Now, notice that resilient modulus is usually an input, right? Input into any analysis. Tell me what modulus I need to use from this picture. There's no single modulus. Give me a stress state that you ran and found that modulus, and I'll give you, again, your modulus value. It's dependent on the stress state. Actually, it's both dependent on the confinement, or we call it first stress invariant bulk stress, as well as the repeatedly applied wheel load stress. So clearly this aspect was, first of all, picked up by Professor Carl Monismith and Dr. Hicks in their 1971 paper. And this is the very well-known K-theta model. But in addition to that, Professor Jacob Uzan and others come up with the effect of the deviator stress should be taken into account here as well. And eventually what formed into a 3D stress space, MEPDG model as we call it, right? Tau octahedral stress was included into this model, and that's the work of Professor Chuck Schwartz. And this is the famous MEPDG model that came into the Pavement ME ASCE design, supposed to be as a level 1, right? So that's the stress dependency we're talking about. We need to take into account in our analysis. The second thing that's most important, and over the years we found this to be truly important, my early work at Georgia Tech, we started looking at that in my PhD, aggregate materials accumulating. These are granular materials accumulating in the vertical direction, sedimentation, kind of think about it. They're already having some of the longer sides or longer dimensions oriented in the horizontal direction. That's what we call as an inherent anisotropy. But imagine the compaction and vehicular loading coming always in the vertical direction. That's further causing an anisotropy. That's related to a stress-induced anisotropy. So indeed, some of the early work I did at Georgia Tech, later on at Illinois, that explained why when you assume a continuum, that granular layer of the base course, in bending under the wheel load, there is horizontal tension, right? Actually, that's what we assume as infinite. It's particulate matter. How is it going to take tension, right? So it's related to the anisotropy. We need to take anisotropy into effect. How can you do that? Here is a FES cell, the University of FES cell, SVD custom designed, but there are similar devices called red cell that allow you to actually be able to pulse in 2 different directions on a specimen, vertical direction as well as horizontal direction. If they're independently controlled, now you can come up with any kind of dynamic stress state, typically under a moving wheel. Or you can just cycle in one direction and test the material and now change the pulsing direction completely on a compacted aggregate specimen, which you should. Otherwise, I know Professor Jerry Leonard's in his career early on, he was able to orientate the specimens 90 degrees to look at anisotropy in clay samples, right? But unbound aggregates confined, you can't do that. So you need to switch the stress states around. That's exactly how we were able to test for anisotropic modulus properties. So that's what this device allowed us. It also allows us to apply various dynamic stress states under a moving wheel load. We call it variable confining pressure stress pads and stress pad testing, right? All these things are important. First on the anisotropy. In 1999, when we did look at the first aspects of switching the pulsing direction on a specimen, right? When we ran isotropic stress strain equations, but whichever direction you're pulsing from, you should be able to, if the material was isotropic, like a rubber specimen you see we tested as a neoprene, it's not stress dependent, and from either vertical or horizontal pulsing, it's giving you a constant modulus, right? That's perfect material, rubber. But nothing like that is our aggregate materials, especially compacted out in the field, right? There's always a higher modulus attained in the vertical direction than the horizontal direction. Horizontal to vertical modulus ratio is the anisotropy, as we always talk about, and this is something that we proved. Further work on that, I was really fortunate to work with two great, again, lecture award winners here, Professor Bob Litton and Dallas Little, whom I respect utmost. Our work through the International Center for Aggregates Research brought out aspects, actually, of the stress dependency for the vertical modulus, but in addition to that, how we were able to characterize this anisotropy of the modulus. That is, typically about 1/4 of the vertical modulus we found, again, stress dependent, but really in the horizontal direction. If you take into account the proper anisotropy of the material as it's compacted, then it is possible to do a much better prediction of pavement responses in your analysis. Some proofs of this. Professor Stokke from Texas went over to a Morgan County haul road. This is a quarry road that was constructed, and did his seismic testing measurements on a constructed aggregate layer, vertical versus horizontal. You can clearly see that. This was published back in, again, 2003. Vertical is higher as constructed in the field. Professor Yad Masad, with his family members who worked on this, looked at and analyzed the Asher road test data for some of those major deflections to match from our models, right? What should be an isotropy, or is it isotropic, giving us best results? When he tried the isotropy here, again, not really. Measured versus predicted, they don't match on the 45-degree line. When we go all the way to horizontal modulus is 30% of vertical, that's when we get the match. I mean, this is something from actual field data as validation of the anisotropic behavior. Further on, in 2007, we did similar validations with some test sections we constructed at Illinois, and actually different thicknesses of base courses tested under moving wheel load conditions of Atlas, and with 170 plus instruments put into as strain gauges, LVDTs for deformation measurements. If you look at those individual responses at once, collected and predicted from our analyses, okay? This is Dr. Kwon's work, really. You can clearly see that predictions with the anisotropic assumption is working much better, and several of those pavement responses predicted at once. If you can match so many of those at the same time, that tells you that you're probably getting the mechanics of how pavement is deforming, right? So this is really a great, great indicator here. So from that perspective, anisotropy is certainly a quality indicator. And we have told this to aggregate producers, we've told this to construction managers and site managers on how to select their aggregates. And as aggregate material basically gets better, higher quality with more crushed, actually better gradation, of optimum packing, dense graded, you can clearly see that that N number, horizontal to vertical modulus ratio, is going up towards the isotropic, making this material stronger. What that does is critical pavement responses, as highlighted, the strain at the bottom of the asphalt responsible for fatiguing of asphalt. right? Or vertical strain or vertical stress, wheel load stress on top of subgrade, controlling subgrade rutting. They're all actually coming down as the anisotropy is getting better. That means isotropic assumption is not conservative, by the way. This is really something we use all the time. Certainly, there are the effects of the percent crush and percent fines on the modulus. As you get a higher crush versus uncrushed material, crushed material usually interlocks better and will give you much higher modulus. That's what you see on the left-hand side. On the right-hand side, what you're seeing is that how much fines, passing the number 200 sieve, I should have in my dense graded aggregate base. Very important question. When you start increasing those, you start to compromise actually the large aggregate contact and the skeleton, the stone-on-stone contact, right? You can clearly see that modulus also goes down with excessive fines, in this case up to 16% fines. On the crushed aspects, crushed versus uncrushed, or rough surface texture versus smooth surface texture, 2 decades of my work, including Professor Massad's work here, we looked at how can we quantify with indices from imaging, image analyses, actually aggregate shape properties, such as, instead of saying angular, subangular, how can I come up with an angularity index? How can I come up with a surface texture index? And this is the aggregate image analyzer developed at the University of Illinois that can do that for you. Why quantifying is important now? Because you can relate it to modulus, permanent deformation, some of these aspects. You can clearly see that resilient moduli here is shown as a function of a composite AI angularity index or composite surface texture index of what kind of properties of aggregate? Well, different blends of crushed and uncrushed materials. You can clearly see that as you go higher in angularity, as you go rougher in surface texture, you're always increasing your modulus. It does a better interlock. Now, let's come to moving wheel load topics. In the case of moving wheel load topics, a state-of-the-art facility that was constructed in the beginning of this millennium is Federal Aviation Administration's National Airport Pavement Test Facility, where they actually can put actual gear loads of the actual wide-body aircraft, like a Boeing 777 or 747, right, and test full-scale pavement test sections. When we looked at some of the data, I was fortunate to be able to analyze some of their data and look at the results and using all the different theories to predict the stresses and all that. How does that compare to what current test procedures allow us to characterize modulus, right? First of all, heavier loads like gear wheel loads of aircraft, very high. And if you look at the middle portion where it shows the middle or the bottom of the base, you see not exactly a stress path slope of 3.0, which happens to be constant confining, but a variable confining because moving wheel load aspects are important. Actually, that NCHRP 1-28A is probably the best in that case. And surely, you can bring those aspects together in a moving wheel load scenario where you see actually when the wheel load goes around and that wheel load is not changing the overburden, but it's according to the dynamic loading, you see the orientation of the principal stress axis, right? And approaching and departing loads, think about how shear stress reversals are happening and how those have detrimental effects. Extension, compression, extension type loading. And many people have shown this over the years, and we need to take this into account, the principal stress rotations, through stress path testing. You can do this by actually pulsing in different directions on a specimen and come up with the right stress states all the way from just pulsing in the vertical, we call it the stress path slope, Q over P about 3, right, constant confining, to going pulsing only in the horizontal direction. And fast cell-like devices or red cell can help us with doing this, actually. Why is it important? Simply, all the compression type loads that you see on the positive axis, Q axis here, are given moduli often much higher than the extension states. Extension states are realized during a moving wheel load. Remember that. Now, why is this important? Probably the most significance of this is in the most important performance indicator of these layers, which is rutting, permanent deformation, right? Here is the phenomenological curve that we are always familiar with, number of load repetitions of the vehicular traffic passing. You see n is the number of load repetitions, and as n is increasing, rutting is increasing, and finally there's an unstable zone where you introduce some moisture maybe to your pavement, right? All of a sudden, right? That's the kind of thing really that was observed over the years, starting from the 1970s. And that phenomenological model that relates to permanent deformation accumulation was thoroughly studied on aggregates first and presented in 1972 by Professor Dick Barksdale at Georgia Tech. This was presented in his third ISEP conference in London. But then it wasn't until 1975 when Professor Carl Monismith finally published this and finally actually gave this kind of a permanent deformation model an expression. Truly, that expression is something that we are using to quantify permanent deformation accumulation. However, more or so in other standards, not the ASCE or not ASTM that are used here in the United States. We still have no well-established test procedure for testing the most important performance indicator of these layers, permanent deformation. You see on these plots the aspects of how stress increases, deviator V-load stress, permanent deformation is increasing, and it's more like V-load compared to confinement, you know, where you get that sigma 1 to sigma 3 ratio, principal stress ratio highest, that's when you are really accumulating at a very rapid rate permanent deformations. You can clearly see in a model like that, the first A parameter or constant really is responsible for, if you haven't done enough shakedown on your material during construction, you can accumulate when you open the road to traffic, very quick permanent deformation, right? Whereas the other B exponent governs the rate of accumulation. But still, this expression doesn't have in it stress terms. We need to include the stress terms into the picture. That's where comes the work, actually, that we have done over the years with FAA's materials. And you can clearly see as you go to including both deviator and confining stress effects, you're reaching a much higher R-squares in a model like that. So you need to be taken into account, all those. One other person I will mention here is Professor Andrew Dawson from Nottingham. Again, beginning of this millennium, he's done a great work on the shakedown material, shakedown behavior of these materials. And clearly an A regime here is first accumulating during construction, and now you open the road to traffic, stable permanent deformation accumulation, right? That's how the road's supposed to last 20 years. Going into B and C regimes, you see there's plastic creep, incremental collapse. And that's how proper compaction is very important on this material, right? And you can put things into perspective on a QP plot as different ranges, typical A, B, C range behavior of these materials in permanent deformation. And what most Europeans do, they also follow a very nice multi-stage testing protocol on the materials, which we have done in this case on a recycled concrete aggregate, which has the lowest permanent deformation actually, and also looking at the rate of strain accumulation. And you can see the next one in blue color is virgin material. So RCA is doing better than even the virgin material. But when you blend the two, you get the worst effect. Now, there are more aspects about that, but this is the way to study the material. This is the way to incorporate stress states, definitely in your permanent deformation accumulation models. This is one we developed based on the simple Moore-Coulomb law. That is the Moore-Coulomb principle of our basically understanding how and where you are in a shear stress, normal stress diagram here when you're about to fail a specimen, and when you're close to failing a specimen when you accumulate so much more rutting, right? So if you put a term then in perspective here as a shear stress ratio, tau F to tau max, tau F is your mobilized shear stress on that failure plane, that's really what governs here. as we clearly apply this technique to practical applications and implications. Depending on your deviator stress you expect from typical wheel load stresses on a pavement, you can actually pick the quality of the material, whether or not that material used in a granular layer will rot or not, right? That's exactly the kind of approach as I mentioned in this case. And the rule of thumb is usually keep that ratio below 0.6 or 60%, right? Now, on the moving wheel load effects, what do you expect? Is stationary loading on a specimen, like a plate loading, or what we are doing with constant confining on a specimen in the lab, or a moving wheel load? Which one will accumulate higher ruts? Through the accelerated pavement studies, people have investigated this for years. You see in the picture Professor Carl Monismith, much younger, in 1972, in a conference in London with Professor Steve Brown and Peter Pell. From their 25 years of studies in the Nottingham Pavement Test Facility, what they noticed was that when they take into account the moving wheel load effects, those are the dashed line ruts that you see as opposed to the same number of load repetitions on a plate load, right? Huge difference. Guess what? In the year 2000, the same thing came from the French. They have a circular test track, and they constructed exact same granular base thicknesses. One is under moving wheel load around the circle. The other one, the plate load, the same number of load repetitions. Guess what? Moving wheel, actually 3 to 4 times higher permanent deformation again. So this is a very important concept here. And in this case, we need to really take into account these stresses beneath a rolling wheel. And when instrumented in a track like FAA's, you can clearly see there's an extension, compression, extension state on the vertical, horizontal, and the shear stresses, right? So it's almost like the same thing we have seen on a QP plot. These are actual measurements from a moving wheel load. You go into extension and come back on the positive compression side on the Q axis, and typical moving wheel load repeats this pattern. That's something we never do. We only use compression loading in the lab, right? But when you take into account actually as one pass of a wheel, extension, compression, extension loops, just like you see as formulated in one of our papers, you can clearly see the accumulation of higher permanent deviatoric strains and volumetric strains. Again, this is very important, moving wheel loads. One other thing that's very important in airport pavements, I don't know if you ever thought about this, but the different gear configurations of the planes, usually there are different points. There's a wander pattern. There's a much bigger wander usually in airport pavement loading than highway pavement loading with narrow lanes, right? In that case, that's exactly what they've been studying in the FAA's facility and understanding how a large rut crater will develop in a wander pattern loading. And you can actually track that. In a study like that, we were able to look at the stress history effects and the shoving and the pushing on the sides of different load locations as it goes back and forth. So we were able to actually predict some of those rut crater patterns. Very interesting. So we have the technology to evaluate these things, and here is currently the permanent deformation model that went into, originally developed by Sang and Litton, the ASCE's mechanistic empirical design procedure, calculation procedure. Note that in the original equation, some of these constants were dependent on the stress states. However, when they eventually put this and implemented in the current ASCE pavement ME, which is used by almost half of the states in this country, that was taken out. However, no worries, there's a newer version of this with the latest work by Professor Litton. Now, he's actually put exactly what I talked to you about, shear strength and stress state effects, back into his equation, hopefully to improve things for us. So that's on a good note. What if those stress states and strengths not accounted for? Again, this is something that you will have as aggregate base may fail in rutting, shear, base, shear, rutting, right? And that's something that you sometimes don't realize, but you can end up with this kind of a scenario. So it's very important to do that proper calculation of the aggregate quality, how thick you can go and where your bearing capacity line fails, whether or not you're rutting these thick layers, and how that's linked to the quality of the material, because friction angle, which is strength, is directly linked to, again, crushed versus uncrushed, and it's not a 50-50 if you come up with a blend. You have to go to very high percentages of crushed to still be able to actually get the friction angles higher up, right? Very important. Another thing is proper compaction, like I said, and proper compaction can be done very nicely on a stiff underlying layer. This is the famous South African inverted pavement design. That's how they can actually achieve compactions up to 105%, right? One last thing, in all of this, how aggregate packing will play a role? Well, aggregate packing or dense graded, people associate that always with 100 years old Talbot's equation, right? Or Fuller curve, Europeans call it. But that usually is giving you many different lines, and with the m value, the exponent, it's not that precise to allow you how you can make your material drainable and stable at the same time. What we have found to give us much better insight through all the optimum packing studies and collaborating with others, looking at the primary structure, secondary structure in the aggregate skeleton, this gravel to sand ratio. It boils down to something very simple. What percent gravel you have in your gradation, what percent sand fraction you have. And the ratio of the two, we found that has to be such optimum that the secondary sands are supposed to provide support to the primary larger aggregate, coarse aggregate skeleton for carrying the load. And through discrete element modeling work with the coordination numbers and porosities and things, we were able to look at that, and GS, G over S, gravel to sand ratio was established like that as 1.6, but typically 1.5 to 2 is where we are actually getting the optimum packing. One other study that looked at both base and sub-base has to do with best value granular materials. I worked on this with MnDOT, Minnesota DOT. Why I'm bringing this slide is very interesting to all of you from the point that where do you put the best quality material? In the base course or down at the sub-base, in the sub-base course? Because, well, sub-base will get lower stresses and all that. Well, that's usually what we think. But for protecting subgrade and minimizing subgrade rutting, it was interesting through all the analyses we did, mechanistic analyses, that sub-base material quality seems to significantly impact the rutting performance. So what you have above your subgrade, that sub-base quality really impacts. What that means to us is that interface between the aggregate layer and the subgrade, there is a really loose contact there. It's not fully bonded at all. That's where the aggregates are spreading under the load, right? That's where you have to really reinforce, stiffen. That's where you have to place some of our reinforcing, stabilizing geogrids, for example, right? That's exactly where geosynthetics are needed, the stiffening effect. This is where Professor Zornberg has been doing a lot of good work, as we have been, and we've collaborated, of course, in those studies. But lateral restraint is known mechanism for this. Immobilizing aggregate movement horizontally under a moving wheel load is a key, and that is provided by geosynthetics for us, minimizing the lateral displacement. And truly, when you do that, okay, here's a cross-section of a pavement we built back in 2007. By doing dynamic compenetration testing down to the depth where you reach, you can see reinforced versus unreinforced or stabilized versus unstabilized. When you come exactly close to where the geogrid is, there is the stiffened effect you can pick up by the sheer number of, basically, number of lobes getting higher. Well, now, more precisely, in our recent work, we have been using Bender elements seismic shear wave transducers to actually quantify that. And for that, first work we did was on providing pairs of shear wave transducers, Bender elements as receiver transmitter, basically to collect the shear wave just above a geogrid placed in the middle in a specimen, aggregate specimen. You can clearly see a mechanically stabilized zone with actual quantified higher shear wave velocities were detected, which relate to small strain modulus values, right? So this is something we need to pay more attention to. We need to also pay attention to moisture effects. As I'm coming close to the end of my presentation here, I cannot leave without saying moisture is always the bad actor for us, right? If moisture is not coming into your pavement, but moisture is always going to get into your pavement, and eventually your dynamic loading pavement system will look like that with the foundation eroding and pumping and all kinds of failures taking place. Again, moisture can come from as precipitation infiltration or capillary rise if you have a shallow groundwater table. These are important conditions. Or it may come all of a sudden as a huge flood for you, right? Flooding effects. This is terrible. This is Florida in 2017. More and more these extreme events. We need to be building pavements that are not going to be eroding completely for you. Roads are lifelines. So this is where really moisture impacts we need to reduce. This slide just tells you that the worst combination is for the moisture effects to take its toll on a granular base. If you have a low quality aggregate, such as high fines gravel, and plastic fines even, and when I say plastic fines, even a PI of 6 is high for these materials, you can have really devastation, high permanent deformations. Moisture ingress, we need to control in design and practice, no doubt. And again, Professor Zornberg has a very nice illustration on how some of the newest geosynthetic products coming out, like the enhanced lateral drainage wicking fabric material, is helping us. You can clearly see the original application of this from the Alaska's Dalton Highway. The dry versus wet you see in the lower right, that's exactly where a wicking fabric was placed. You can see that that's a cutoff for that water line climbing up. Now, related to that, many people have worked quite a bit, including Dr. Zhang from Missouri, but more recently, my good friend, Professor Jihan, has been doing very good work in their lab, both looking at precipitation type moisture coming into an aggregate base as well as capillary rise. And in the case of with the wicking fabric, he clearly showed that permanent deformation can be minimized if you're using the wicking fabric because it is so effective. This woven geotextile has the lines, exact capillary rise type connected lines to actually drain the water for you with the same adhesion principle. So one other interesting one is the same volume change potential control with the moisture goes to expansive soils. Expansive soils in your subgrade or in your base course, you want to minimize the transmission of the flow of the water, capillary rise. Professor Anand Pupala, another good friend here, clearly showed some of this application in his recent work, and you can minimize expansion or expansive potential of a soil by not providing moisture to go up to that level. Again, another excellent use of wicking fabric in that case. One other thing that's important is this aggregate layer intermixing with the subgrade, and often with CBR 1 or 2, very low strength subgrades. This is a concern because aggregates are lost into a pumping subgrade, right? And this is something we studied as part of our aggregate subgrade work at the University of Illinois with and without actually geotextile in this case. And clearly under repeated loading, if you have a soft subgrade, these large rocks, often there to remediate and provide a construction platform, right? They go as deep as 10 inches into that subgrade. This is a 3-year-old concrete pavement. Dr. Barry Christopher's excellent slide collection here. That shows you that aggregate layer doesn't look as good as 3 years ago, right? You know why? Pumping. Again, pumping will happen there. You always need a separation geotextile. Mark Marienfeld usually calls this as permanent road foundation. I'm a true believer that you need to provide a separation layer between your, again, subgrade, minimizing effects of those intermixing. So this will really make the road permanent foundation. Lastly, on this topic, on the moisture and drainability topic, there is always an issue about how good of a underlying layer, support layer, can unbound aggregates provide to slabs, rigid pavements, right? And the issue is usually the drainage in this case. But if you go too open-graded permeable bases, then stability is compromised. You need to have a stable, dense enough layer as well as a drainable layer. How you can do that is what we use as the gravel to sand ratio as a key for us in a recent study. And we were able to show that you can actually come up with a very narrow gradation like that will actually be stable and drainable, and actually with the use of a separation geotextile will be permanent for you, durable. Finally, sustainability aspects, as I promised, going more and more to primary crusher type larger rocks. Larger rocks are very, very nicely used, again, on soft subgrade remediation. And they're out of spec materials. They're not used as layer materials. Recycling of the old pavements and using back in pavement construction. Some of full depth reclamation projects, they all need to go through a certain life cycle analysis, life cycle cost estimate analysis too. We want to make sure your sustainable application will perform at the end. As part of that, we've been studying RAP, large aggregate use, as well as quarry byproducts mixed with large aggregates you see filling the voids of the large stones, and the roller that you see here is actually percolating all the sand-sized quarry byproducts, right, which typically are generated in a quarry operation up to 25% in typical dolomite limestone type aggregate material, and you can actually pack them together into the voids of large rocks, making those layers much more stable. Or you can use that same out-of-spec quarry byproduct and cement stabilization or type C fly ash stabilization. We have shown this to be remarkable. With only 3% cement and quarry byproduct sand-sized material, we were able to build bases and sub-bases that actually lasted so well. And Department of Transportation at Illinois, they wanted to actually do a durability study on this. It was so well cementing, especially dolomite material, that we weren't losing any material weight loss in the weight loss freeze-thaw test. Finally, towards the end here, I'm almost done. I know I'm a little bit over here. Only 5 slides left. All right. Thanks for bearing with me. I have to mention the 800-pound gorilla in the room. This is the disconnect between the design and pavement construction quality, right? What we assume as one value is never the case. That's why our designs, as we improve, we need to do a good job in pavement construction. Or as Professor Marshall Thompson, my colleague at Illinois, always says, measure with a micrometer, mark with a grease pen, cut with an axe. Okay? This is usually what we do out in the field. But we can do better, and we can do better with some intelligent construction practice. Dr. David White, who used to be, again, professor at Iowa State, developed some of these techniques that really help us to go out there and calibrate the intelligent compaction equipment, as well as be able to load now exact same repeated load triaxial testing out in the field on the material, on the constructed material using his automated plate loading test. This is something that I think in the future we need to be doing more as intelligent compaction is coming to our practice. What is also in the future is with the intelligent construction, we need to be doing more smart sensing of these aggregate materials and how they perform. One of my students who is in the audience, great to see him, Professor Hai Huang, came from Penn State actually in this application, worked with us. This is a smart rock, one of his innovations here, which is equipped with, the outside shell is a 3D printed basically, but inside there's basically 22 millimeter of triaxial accelerometers, gyroscopes, as well as pressure cells and pressure reading material with temperature. When you bury this during the construction, you can clearly see under a vibratory compactor how in the vertical and 2 horizontal directions the movement of the roller can be felt. It's not just the horizontal movement. The actually blue lines show the ones on the side are actually rotating a lot. There is rotation that was picked up in that study as well. And this study was actually a really unique one. We collaborated and worked together with the Army Corps of Engineers Engineer Research and Development Center, Smart Runway. Smart Runway that was in the Air Force, Hill Air Force Base, that helped us actually also install bender element sensor. This is a field sensor to measure modulus, but throughout the lifetime of the pavement. And the same thing we installed in the FAA's facility on a first time constructed and tested geogrid stabilized base course section to pick up again the modulus improvement. So these are the things that are coming again as smart sensing in our construction practice. Truly the last slide I will show here before my acknowledgments. I'd like to end my talk, and thank you for, again, bearing with me, by mentioning that all these innovations can come together, and this is a true representation and demonstration of that. Army Corps of Engineers have come up with CFlex, their new Advanced Flexible Pavement Analysis program. And I've been lucky to work with them on that from the perspective of building computational engines into their next generation Pavement JEDI 2D, Joint Evaluation and Design Integrated Software. And the good news is that in that CFlex program, which was an object-oriented programming for us, but modular and extensible features, we were able to bring in all the options of an isotropic and anisotropic characterization of a linear or nonlinear stress dependency, as well as geosynthetics module, as well as superposition aspects of multiple V-load superposition, which works even in nonlinear case, believe me, and you're getting some good conservative results in that case when you're running an axisymmetric solution. This is the type of future. This is the type of analysis we need to be incorporating these aspects. I'm really proud about that work. So, as I conclude my talk here, I would like to, I owe a debt of gratitude, to be the least, to these brilliant faces that you see, as many of my PhD students who actually did the work I presented to you, 25 years of work here on granular materials. And many of them are in the room today, and especially the current PhD students in the bottom row. They're all here. They wanted to drive over here to just enjoy the moment, and I truly appreciate all of you contributing to years of work I've talked about today. Without them, it wouldn't be possible. These are the master's students graduated, but I'd like to also mention some of the bright faces also as postdocs and visiting scholars and collaborators, research collaborators that I cannot name here, as well as sponsors of my research. I'd like to thank all of them for the work we've done. Thank you again for your patience.